For years, AI in software development was synonymous with localized autocomplete, predicting the next line of code based on immediate context. Today, those utilities have been replaced by orchestrated, multi-layered computational systems designed to replicate the end-to-end workflows of a human engineer. This marks the transition from the traditional software development lifecycle to the Agentic development lifecycle, or ADLC. Historically, the volume of code a team could ship was limited by human typing speed and individual cognitive load. Now, autonomous agents can parse schemas, modify cross-service files, and run massive test suites at machine speed.
A language model acting entirely on its own simply cannot hold the state necessary to resolve tasks that unfold over days. At its core, a language model is a stateless inference engine. It takes text in and predicts text out. It possesses no inherent memory, no persistent state, and no mechanism to execute it. To bridge this gap, engineers wrap the model in an agent harness, a heuristic control layer that supplies these missing operational capabilities. An AI agent isn't a monolithic brain. It synthesizes the predictive model core with surrounding infrastructure. The harness intercepts data, parses feedback, and executes tools like an operating system, while the language model serves as the CPU analyzing provided state. Maximizing performance on complex tasks requires a shift in engineering focus. Optimizing prompts yields diminishing returns. The bottleneck is the design of the harness. The foundation of this architecture begins at the interface layer. In agentic systems, code is no longer the final product to be generated. It serves as the operational substrate through which the agent reasons and acts. This substrate has three properties. First, executability. Because code runs, the harness verifies if actions worked. Second, inspectability. As programs execute, they generate logs the harness can diagnose. Third, statefulness. The evolving commit history represents a persistent record of progress. Together, these three properties allow the harness to map abstract natural language into precise executable behaviors that obey the rigid constraints of a software environment. Grounding the language model in this code substrate transforms a stateless text generator into an entity capable of observing and persistently manipulating an environment. Operating in a large repository introduces a physical constraint. The model's context window can only hold a limited number of tokens, while the intermediate state of the software task continuously expands. Dumping an entire execution trace or build log directly into the prompt will instantly choke the context window and bury decision-relevant evidence in noise. To manage this, the harness uses a working memory module to track the active coding context, manage edit states, and budget token slots. When logs grow large, context compaction automatically compresses long interaction histories into structured summaries. Simultaneously, state offloading moves full-fidelity artifacts into external databases, giving the model a compact resource identifier. The model explicitly requests that identifier to retrieve only needed stack frames. Memory in a production harness operates as an active state management layer. It routes, compresses, and persists data to keep the model grounded over long time horizons. Once the agent can maintain state, it requires a secure mechanism to take action. Basic API function calling is insufficient for tasks on the scale of SWE-bench Pro.
The agent needs direct environment interaction through bash shell commands, file editors, and test executors. Allowing an autonomous system to execute arbitrary commands directly on a host machine invites catastrophic security risks and silent state corruption. To mitigate this, actions are confined to a Sandboxed tier. These isolated workspaces fully encapsulate the agent's operations. If the agent generates a destructive command, it executes inside the boundary, fails safely, and leaves the host environment untouched. This strict isolation guarantees that code execution is perfectly reproducible, auditable, and state reversible for the harness. Governed tool interfaces paired with sandboxed execution allow the agent to make high-impact modifications to a codebase without compromising systemic reliability. To understand how these systems function, we must trace the agent's chronological journey from the moment it receives an abstract bug report to the delivery of a verified patch. The system autonomously navigates the repository, plans its trajectory, synthesizes the code, and debug the results without human intervention. This creates a unique engineering challenge, constraining a large language model, a system built on probability, to safely navigate a rigid enterprise codebase.
The architecture relies on the plan-execute-verify loop, forcing the system to separate reasoning from action. In the plan phase, the agent externalizes its intent, creating a blueprint that decomposes the task into executable steps. For complex tasks, the agent uses a multi-path tree search, evaluating candidate solution paths simultaneously to mathematically trace the best route before committing code. Once the trajectory is verified, the flow moves to the execute phase. This is the transition from probabilistic reasoning to deterministic execution. To test its work, the agent must leave its reasoning engine and use its computational body to interact directly with the operating system. This requires a sandboxed environment. The agent executes shell commands and compiles code inside a secure virtual machine, isolating potentially destructive commands from the host infrastructure. Code generated within a neural network is only a theoretical exercise.
Sandboxed execution is what transforms that theory into functioning software. The journey then moves to the verify phase. This is the mechanism by which the agent grounds its guesses in objective reality. The agent triggers deterministic sensors. It subjects the code patch to language compilers, syntax linters, and static security analyzers to check for errors. In the SWE bench framework, the industry standard for evaluating agents, 2 criteria are measured. The fail-to-pass test ensures the fix is effective, modifying logic so original bugs pass. The pass-to-pass test runs new code against existing suites to ensure no regressions are introduced. If a sensor flags a failure, the agent enters an iterative debugging loop. It reads the execution logs, analyzes the stock trace, and revises its code patch autonomously. This cycle of execution, failure, and self-correction is how the agent moves from a probabilistic guess to a deterministic proof. There is a cost to this iteration. As the agent plans, codes, and fails, its historical execution trace grows until it threatens to fill the context window. To stay operational, the system uses context compaction. This is the algorithmic process of summarizing the agent's history to free up space. While basic systems simply drop old messages, advanced architectures use external memory persistence. They offload the repository state to a durable vector database, allowing the agent to retrieve critical context only when it is needed. Even with optimized memory, a single agent will eventually hit a computational limit when managing massive, cross-service enterprise tasks. Scale is achieved through multi-agent topologies, distributing workloads across architects, coders, and verifiers via an adaptive directed acyclic graph. Data shows these are highly effective. When a node detects an error, the topology dynamically reroutes based on feedback to find a solution. True autonomy is the result of an orchestrated ecosystem where specialized entities collaborate within a highly structured workflow. Once the agent's iterative loop satisfies the automated tests, the final code artifact is prepared for the repository. However, high-risk changes often trigger a human-in-the-loop protocol. The autonomous pipeline pauses, and the patch is sent to a human engineer for review. This introduces the verification tax. Because the agent's internal reasoning can be opaque, humans must spend significant cognitive effort auditing the machine-generated logic for subtle errors or architectural misalignment. The data reflects this burden. AI-generated pull requests average 10.83 issues per PR, compared to 6.45 for humans. Critically, issues related to code readability increase by over 3 times. The organizational bottleneck has shifted. The time saved during the coding phase is now frequently respent during the auditing phase. This shift also changes the nature of security. Traditional frameworks scan code just before deployment, but in the ADLC, risk enters the system the moment the agent begins calling tools. Securing these workflows requires real-time controls across 3 vectors: the inputs the agent uses, the actions it takes, and the outputs it generates. Actions are high risk. An unconstrained agent might autonomously alter a production database schema at machine speed if it isn't properly restricted. Reliability depends on wrapping the entire execution sandbox in zero-trust permissions, ensuring the agent possesses only the minimum privileges required for its specific task. In this environment, the role of the engineer is redefined. They are no longer just writers of syntax. They are the macro-level governors of an autonomous architectural system.